So welcome to Math317 Operations. This is lecture 23. And so what I want to do today is talk a little bit about the differences between constructive and non-constructive methods and start some applications to some of the biggest results in operations research, some methods that will guarantee us that certain types of solutions exist. The problem, of course, is whether or not we will be able to find such a solution. If you are trying to staple, you can probably remove a staple from the exam and then use that as a staple for your test. In this class, have we done the intermediate and the mean value theorems? I know I did them in problem solving. I don't think I've done them in this class yet. All right. These are, to some extent, the no-shit theorems from calculus. These are big results, and they are extremely obvious when you think about it and you think about the conditions. So the first is the intermediate value theorem. And this says if we have a continuous function on a closed interval AB, and C is any number between f of A and f of B, then there is some number C in the interval such that f of little c equals big C. What this is saying is you cannot discontinuously jump from one point to another. If I'd been feeling better, sadly battling a stomach ache, I would have dressed up as Spock today for Halloween. One of the big inventions in Star Trek is the transporter. What does the transporter allow you to do in Star Trek? Okay, but lots of things allow you to get from one place to the other. What does the transporter allow you to do? Instantly. And the reason the transporter was created is they didn't actually have a budget for a shuttle in the original premiere. So since they couldn't afford a shuttle, well, what if we just push this button and then all of a sudden appear on the planet's surface? Then we don't need to build that prop. If you have a discontinuous function, you don't expect the mean value, the intermediate value theorem to be true. You could be 0 all the way up to 1/2 and then jump up to 1 from that point onward, and you wouldn't hit anything intermediate. It is a nice exercise to try to prove the intermediate value theorem rigorously. When you take a calculus course, you should have seen this result. I don't know if they proved it. And so what you can do is you can try to prove it by using continuity. What you can do is you look at the point, let's say we're trying to show that the function is 0 at some point. So I'll just, let's say proof the intermediate value theorem. So let's say we have some interval. Let's say the function is negative at 0, positive here, and we want a c such that, say, f of c equals 0. What we can do is we can do like a divide and conquer. We can look at the midpoint 1/2. If the function is positive, then we'll look somewhere between the intervals 0 and 1/4. 0 and 1/2. So let's say we look at 1/4. Let's say it's negative there. So we look at somewhere between 1/4 and 1/2. What's halfway between 1/4 and 1/2? 3/8. And let's say it's positive here. So what we would have is we would have a string of upper bounds, B1, B2, B3, such that B1 is greater than or equal to B2 is greater than or equal to B3, and each f of bk is greater than 0. And we would have lower bounds A1, A2, A3, ... such that they're non-decreasing, and it's always less than 0 there. So we would have a string where it's negative from one side, positive from the other. Well, maybe at one of these points it actually equals 0. Well, if it equals 0, we're done. So I'll put maybe greater than equal to less than equal to 0. So now you have a string of 2 sequences. What do you know about the A's and the B's? What do you know about the limit as k goes to infinity of ak and the limit as k goes to infinity of bk? What must be true about these limits? So ak is the lower bounds, bk is the upper bounds. So how far apart are A0 and B0? 1. How far apart are A1 and B1? 1/2, and so on and so on. So we know the distance between them is tending to 0. The A's are strictly increasing, so the A's are non-decreasing, the B's are non-increasing. They're going to be equal in the limit, and it will be some common value. Anybody want to guess what that common value should be? So what should we denote that common value by? That's the C we're looking for. Because if we look at the string from the A's, the function is negative, 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 negative. And if we look at it from the right, it's positive, 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 positive. And so because the function is continuous, this is C, use continuity at C. So there are 3 possibilities for the value of C. What are the 3 possibilities for the value of C? Zero. What else? Nope. Nope. So there's 3 possibilities. F of C could be 0. What are the other possibilities? It's going to be very general possibilities. One possibility is it's 0. Another possibility is it's positive, and the other possibility is negative. So case 1, F of C equals 0, done. Case 2, F of C is greater than 0, then there exists a delta such that if close to C, F of X is still going to be greater than 0. Because the function is continuous, let's say F of C is 1 over billion. Then I can take my epsilon to be 1 over trillion. And if I'm sufficiently close, then my function has to be positive there as well. And so you get a contradiction as F of AK is less than 0. And in case 3, F of C is less than 0, similar. So this is a sketch of a proof of the intermediate value. This is one of the big results in calculus. One of the big consequences of this is Rolle's theorem, which is a special case of the mean value theorem. So the mean value theorem says if we have a continuous differentiable function, then there is some C in the interval AB, such that G prime of C times B minus A is G of B minus G of A. Or another way of looking at this is G prime of C equals G of B minus G of A over B minus A. This is the average speed, and this is the instantaneous. Has everybody seen the mean value theorem? That at some point, the average speed is the instantaneous speed. The simplest way to prove this is to use the intermediate value theorem. Assume that you are always traveling at the average speed. Can you give me a time when you're traveling at the average speed? Anytime, right? It's really easy. So the only thing that's left is we can't always be traveling at the average speed. So without loss of generality, assume at some point we're traveling faster than the average speed. Could we always be traveling faster than the average speed? No, why not?
Just pass through the average speed.
Well, I mean, I could start off at, maybe my average speed is 50 and I could start off at 60. So not, but what would happen if I'm always traveling above the average speed? Well, so if my average speed is 50 and I'm always traveling greater than 50 miles an hour, what can you tell me about my average speed? It's greater than 50, right? If you're traveling faster than the average speed at every moment in time, that can't be your average, because the average is basically the integral of your speed divided by the length of the interval by the time. So we know that if we're traveling faster than 50 miles per hour, the average speed, at some point we must be traveling slower than 50 miles per hour. So now we know at some point in time, we must be traveling faster than the average speed. At another point in time, we must be traveling slower than the average speed. So what can you now deduce? Good, why? So why must there be some point now where the instantaneous speed is the average speed?
Your speed is like your function of just speed over time.
Right, now we can use the intermediate value theorem. And this is why we have a continuous differentiable function, and this is why the mean value theorem is coming after the intermediate value theorem. And that's why we did the intermediate value theorem first. One of the most important consequences of that is the mean value theorem. This allows you to approximate a function. If you know where you start and you know your instantaneous speed, a short time later, a good estimate of where you are is where you started plus instantaneous speed times elapsed time. The more time passes, the less likely this is to be a good approximation. Okay, but this is one of the big applications. Think of it as the poor mathematician's Taylor series. This is the tangent line from calculus. Now, it's important to note that in these theorems, we have phrases such as there exists. It is not constructive. It doesn't tell us how to find such a point. It also doesn't tell us if the point is unique. There might be multiple points that work. Do you remember the contraction maps we did? That if you have a contraction map, there's a unique fixed point. Do you remember how to find the fixed point? So how would you find the fixed point? Yeah, you just choose any point at random in the set, and then just keep applying your function. And let's let xn plus 1 be f of xn. You just choose a random point and keep iterating. So for the contraction map, not only is there a fixed point, not only is it unique, but we have a way to find it. Choose any point and keep iterating. Okay. Intermediate value theorem, mean value theorem, they don't tell you how to find the point. Now, if you look at the proof of the intermediate value theorem, we actually have a constructive way to find it. Start at the left and right endpoints, bisect it, and keep going like that. We can actually make this constructive. So a lot of times you might have a theorem that is proven in a non-constructive way, but you can make it constructive. All right. What I want to do is I want to talk a little bit about some non-constructive ideas, because this is a big thing when we're trying to solve problems. Step one is prove a solution exists. Step two is to find the solution. If there's no solution, it's not worth trying to find it. So this is the game dots. It's sometimes called Chomp. The way it works is you have a rectangular grid of dots. And if you choose some dot, let's say we choose this one over here, then you eat from here up and from there to the right. So if I choose any dot, I just see all the dots above and to the right. So initially, the first person is going to eat a rectangle in the upper right corner. Whoever eats the last dot loses. Why don't you want to play the game with whoever eats the last dot wins? Why would that be a very boring game to analyze?
First person can choose the bottom.
Yeah, first person would just choose the bottom left dot, game over. Want to play again? And so the only chance of having an interesting game is whoever goes last is the one who loses. And so the question is, who has the winning strategy? And how does that depend on the board? Well, it turns out player one always has a winning strategy. And so I'm going to show you that if player one plays intelligently, they can always win. What would you like to know once you know player one has a winning strategy? What is the winning strategy? I can't tell you. It is a non-constructive proof. And so there's two cases. Consider a given board. For this board, either player one has a winning strategy or they don't. If player one has a winning strategy, I don't have to show you that player one has a winning strategy. So let's assume player two does not have a winning strategy, and let's get a contradiction. So player one, I'm going to have them initially move in the upper right corner. Because player one doesn't have the winning strategy, who has to have the winning strategy? Play two. This is a finite game. Someone is going to win. Is it possible for this game to end in a tie? No. So I know some of you have been playing chess recently. It is possible for chess to end in a tie. Lots of games can end in a tie.
Chess ties are really annoying though, especially if you like get them in a position where
The threefold repetition.
I was gonna say where they're not in check, but they don't have any other moves.
Right. So there's a couple of interesting ways to get a draw in chess. This will not happen in this game. Someone has to win. Now, tic-tac-toe, it's possible to fill up the board in tic-tac-toe without anybody winning. And in fact, if you play intelligently, no one should win in tic-tac-toe. So imagine player two has the winning strategy. Player one takes the upper right corner. That means player two has to have a move that continues the winning strategy for them. So I have to choose something because I am showing this on the board. Let's say this is where player two needs to go to continue their path towards the win. Again, I don't know it's this point. I'm just, for definiteness, I have to draw something. How many of you have ever played games with a little kid? So imagine player one is now one of those annoying little kids. Oh, no, I didn't mean to do that. That wasn't my move. I want to move where you move. That's what I want my first move to be. And I'm making that my first move, and you can't stop me. So player one has changed their mind, and they want this to be their first move. Well, if we assumed that player two had the winning strategy, when we had this configuration, after player two moves, they have the winning strategy. So the person who moves next is on the path to defeat. So if player one now changes and now moves like this, they've now done a parity switch. And now player two is the one who moves next, and player two will be the one who's on the path towards defeat.
Can you explain the game again? Like I'm not.
So when you choose a dot, you eat all the dots from that point up and that point to the right. So over here, the player one chose the upper right corner, so only one dot was eaten. Player two chooses, if we start the bottom is row one, they chose row three, column four. And so they would eat everything above and to the right of the point at 3, 4. And whoever eats the last dot loses. Okay. And so when you look at it like this, player one has the ability to do a parity switch and take over from player two. And so now player one has put player two into the losing position. Therefore, our assumption was wrong that player two had a winning strategy. But player one has the winning strategy. This is entirely non-constructive. I can't tell you how it's done. But what I want you to get from this is there are certain games where we can't tell you how you should play to win, even if we know who will win if you play correctly. We want to find optimal solutions to problems in life. Well, if we can't find optimal, we at least want to find good solutions to problems in life. If you can't find the optimal solution, can you at least find a good solution? Well, step one is to prove that such a solution exists, and then the next step is to try to find it. So what I want to introduce is a game that I will call the triangle game. And I will play the class, and I will put $100 on the line. Right? I can play either US, Canadian, or Mexican. I have money from all 3 countries so that no matter where I'm driving, I can always have some cash on me for wherever I end up, because I have to flee quickly. So here's the rules. The 3 vertices are labeled 0, 1, 2. The bottom, you can only label the vertices with a 0 or a 1. The right side only with a 1 and a 2, and the left-hand side only with a 0 and a 2. And you and I have to label all the vertices. My goal is to make sure that one of the small triangles has a 0, 1, 2 labeling. If you look at the giant triangle, it has a 0, 1, 2 label, but that's not one of the small triangles. How many small triangles are there? I think I counted 16. So you have to show that you can prevent me from making one of the 16 triangles have a 0, 1, 2 label. If you can come up with a way to assign the labels, I will give you $100 if we alternate moves. So you go, I go, you go, I go. I will give you $50 if you do 2 moves and then I get 1 move. Why do you think that's only worth $50? You have a clear advantage, right? I will give you $25 if you get 3 moves for every move of mine. $12.50 if you get 4 moves. So how many moves do you want to choose?
I'll say 2.
2? This has to be a class decision. You guys win and I will pay up. 2. All right, where do you want to go? Bottom left. Okay, what label do you want to put there? All right, so you want to do 0, 0. Oh, actually, the whole reason I did this was so that I could put the stuff in different colors to make it easy for us to tell. All right, I'm gonna use thick. All right, where do you want your next one to be? So first row, second row, third row, fourth row. Where do you want your next one? I'm sorry? I mean, again, you can discuss amongst yourselves and you can.
Start eliminating trouble.
Yeah, I think it makes sense to go off.
So you want this one?
Yes.
Okay, what do you want that to be?
I think it only makes sense to do 0.
Has to be a 0, because if you put a 1 or a 2 there, I can win. All right, now if you go there, if I go 1 to the right of that, if I put a 2, I'm threatening you with a 1 there, and I'm attacking you in 2 different places. Now you do have 2 moves. Do you want to do 2 moves to my 1 move, or do you want to do 3 moves to my 1 move? All right, bring it on. I'm going to go here with a 2. So I'm attacking you in 2 different spots now. So your 2 moves are forced unless you're complete morons. Given that you're at Williams College, you are not complete morons. So you have to put either a 0 or a 2 down here, right? But it has to be a 0 or 1. So you have to put a 0 here. That move is forced on you. Yes. I don't know if the iPad audio can pick that up. We'll see. So now you've got to go up here. You've got to put either a 0 or a 2. If you put a 0, that might be helping me up there. I don't know. If you put a 2, that does prevent a lot of trouble. But if you put a 2, what will I do over here? 1. So you have to put a.
You can't put a 1 on that left side, though.
Oh, so you. Well, I'm saying you have to go over here, or I win. Yeah, I will put a 1 above the 0, 2 triangle. So you've got to go there.
You already win anyway, though, because the bottom.
Oh, in the bottom, I'm going to put a 1 there in the next turn.
Yeah.
So why don't I let you do 4 moves to my 1 move, starting now? All right. So what do you want to put? So you want to put a 0 down here and stop that, right? And then we've got a 0, 2 triangle over here. We can't have a 1 here. So you've got to put a 0 there. Right?
It's gotta be a 2,
Oh, sorry, it's got to be a 2. Sorry. Got to be a 2.
but you win with that. So
And I win, and I win. And so I'm going to just have some fun by coloring this in all these different colors.
This is an awful game.
What do you mean it's an awful game?
You can't win.
Well, it just means you can't win this time. Now, we could have continued. Unfortunately, I ran out of space. $12.50 if you get 4 moves to every move of mine, to eventually you get $1 if I don't even move. I'm willing to play this game where I'm not even going to move at all, and I will let you do all the moves. What can you deduce from the fact that I'm willing to play this game without moving?
But it's
There's no way you can configure the board how to 0, 1, 2, and 1.
Right.
We saw this.
Yeah, this is Sperner's lemma.
Yeah,
It's a beautiful result.
yeah.
So no matter how you triangulate,
Oh, you're right.
there's always going to be at least one triangle that is labeled 0, 1, 2. And so in this particular occurrence, there actually were 3 triangles. Now, if I'm able to win without doing any moves, my strategy has to be really simple on defense. What's my strategy? Just play. I don't have to do anything. Just, it's rigged so I will win. I've done a lot of math in the elementary schools, and as the kids get older and older and older, and they see me visit more and more often, they realize every game is rigged. And so last year I was visiting the 6th graders, and they actually formed a group and they met over recess for several days to try to come up with their own rigged game to play me. And so I went back and we rumbled. They made a small mistake. They had the advantage, but I was able to take them down. But a lot of fun, absolutely tremendous fun. Before we understand this 3-dimensional game, this triangle game, what might be an easier game to study? So again, a lot of times you're given something in life that's a very complicated problem. And this is what people want to solve. That's fine, but that's not what I want to solve first. I want to solve something else and build intuition. What might be better than studying the triangle game? What might be a simpler version?
Squares.
Okay, but square would still be like a 2-dimensional game. A line. So we could play maybe the line version. I've got a line segment, I've got a bunch of dots, and I want to label it in such a way that there's at least one segment with a 0, 1, on the endpoints. And if I can do that, I win. If I can't do that, you win. Okay? So here's the claim. Always at least one segment is 0, 1 or 1, 0. And the proof is really straightforward. So let's imagine we have a bunch of dots. So you are trying to prevent there to be a 0, 1 labeling. At least one of these dots, you should be able to tell me immediately what it must be labeled. Which dot is that? Yeah, what does the one immediately next to the 0 have to be? It has to be 0. Why?
Otherwise that's a 0.
So these all have to be zeros. What else do you know? Oh, I'm using green for zeros. Oh well. Yeah. And so what are the ones next to the 1 have to be? They have to be 1s. So you have the march of zeros from the left. You have the march of 1s from the right. And that poor little dot in the middle has to be labeled both 0 and 1. So there's no way to stop. So this proves that there will always be at least one segment labeled 0, 1. Okay, anybody know what college football team I root for? Of course I root for Williams and Yale, my alma maters, but no, not Ohio State. It's not Ohio State. What is it? The Ohio State University, right? There is one and only one. In math, we normally don't have the. We don't talk about the proof, we talk about a proof. This is a proof of the result. There are other proofs, and in fact, some of the other proofs are better. So let's imagine we have 3 different possibilities. We have a 0, 0 segment, a 0, 1 segment, and a 1, 1 segment. And we put a new point in between all of them. And we see what happens. Well, the new point could be labeled either 0 or 1. On the left, we had a 0, 0. When we put in a 0, we still have no segments labeled 0, 1. When we put in a 1, we now have 2 segments labeled 0, 1. For the other one that was 0, 1, when we put in a 0, we still have one segment that's 0, 1 as before. When we put in a 1, we still have one segment as before. For the third one, if you just flip all the 1s to 0s and all the 0s to 1, it's the same case. So what we notice is every time we add a new label, the number of 0, 1 segments is either the same or changes by 2. So as add points, the number of 0, 1 segments is never changed mod 2, right? It always stays the same because we either add 0 or we add 2. We don't change its remainder when you divide by 2. Initially, have one segment that is 0, 1. Whoa. Oh, crap. Oh, okay, great. Okay. So somehow we should. Okay. As initially, one segment is 0, 1. At end, what must be true? What must be true in the end? So if we start with one segment that's 0, 1, what must be true in the end? There's at least one. Why? What do you know about the number of 0, 1 segments at the end? Have an odd number of 0, 1 segments. So at least one. So this is a absolutely beautiful result. One way to show something exists is to show that the number of objects is odd. And since the smallest odd number is 1, well, non-negative odds, the smallest non-negative odd number is 1, if you know something is odd, then it has to occur. So this is a beautiful proof. Now, do we agree that this game is boring? So you could try to make this game more interesting. What you could say is, look, I know I'm at a disadvantage if I'm playing defense because you're going to get at least one 0, 1 segment. So maybe what we'll do is we count how many 0, 1 segments there are and we subtract 1. And then see if you can beat me. And you take away the fact that we know you have to have 1. So again, whenever you see something, always be thinking, how can you generalize this? If the game is not fair, what do you need to do to make somebody willing to play? Okay, so now let's go back to this lemma. So we want to show always have a 0, 1, 2 triangle. Okay, and again, it doesn't have to be cut like this. This is just a picture that I can somewhat draw with my limited artistic abilities. And so these are 1s and 2s. These are 0s and 2s. These are 0s and 1s. One of the big ideas in mathematics is building up from small cases. So right now, this doesn't really look like perhaps a topic that's worthy of an entire math lecture. This is one of the keys to what's called a fixed point theorem. And these have tremendous applications in mathematics and economics. So we can use these to prove a lot of things. What do we know about the bottom? So as we put in our labels, what do we know is true about the bottom? It's only made up of 0s and 1s. What else do we know?
There's at least one 0, 1 segment.
There's at least one 0, 1 segment. What else do we know?
When we put in numbers, the number of 0, 1 segments increases 1, 2.
Good. So what do we know about the number of 0, 1 segments? It's odd. Okay, so these may not be useful, but these are at least facts that we know. So what we can do is let's count the number of 0, 1 segments. If you consider the perimeter of the triangle, what can you tell me about the number of 0, 1 segments on the perimeter of the triangle? Are there any on the 1, 2 side? Are there any on the 0, 2 side? And what do we know about the number on the 0, 1 side?
So not count if there was like a 0 on the midpoint.
I'm just counting the perimeter. I'm just counting the perimeter. Just counting the perimeter. So what do we know about the number of 0, 1 segments in the perimeter?
There's at least one.
There's at least one, but more than just there's at least one. It's odd. So the number on the perimeter of the big triangle is odd by last problem. So this is promising. We're using a lower dimensional case and building up from that. We know the result in one lower dimension. Let's see if we can build that up, bootstrap that up to something higher. So now let's look at triangles that have labels. Which triangles are going to contribute a 0, 1 segment? So we have, what kind of triangles can we have that could contribute a 0, 1 segment? Which triangles would have a 0, 1 segment? So give me what their labels would be.
Zero is when you could do like the one to the left or the right.
Who give me a triangle that would have a 0, 1, 2 segment? Give me its labels.
0, 1, and 2.
Okay, so 0, 1, 2 gives how many? 1. What else could contribute a 0, 1, 2 segment? 0, 1, 1 gives how many? Gives 2. Because no matter how you put the labels, 0, 1, 1, you're going to have 2 segments that are 0, 1. What else could contribute? 0, 0, 1. Does anything else give a 0, 1, 2 segment? That's the only ones that will give a 0, 1 segment. So let Tijk be the number of triangles with labels I, J, K. How many 0, 1, 2 segments do we have? Well, the number of 0, 1, 2, so the number of 0, 1 segments we have is going to be a function of the labeling. And it's going to depend on how many triangles we have. If we have an internal label, an internal edge, how many times are we going to count that 0, 1 segment? Twice. So internal 0, 1 count once. I'm sorry, count twice. Boundary count once. So does everyone agree that the internal segment is going to be on 2 different triangles? So if I look at this one over here, it's on 2 triangles. It's on this triangle, it's on this triangle. But if I take the segment down here, it's only on 1 triangle. Right? All right, so let's count the number of 0, 1 segments. So we take the T 1, 2, 3 triangles, and each one of these gives us how many? Oh, no, 1, 2, 3, sorry. When my son was very young, he learned that if I told him you can do something 3 more times, to start counting with 0, because daddy's a mathematician and daddy will find it amusing. We start out counting with 0, not with 1. So for the 0, 1, 2 triangles, how many 0, 1 segments does that contribute? 1. And then the 0, 0, 1 triangle, how many 0, 1 segments does that contribute? 2. And then the 0, 1, 1, how many does that contribute? 2. Is this equal to the number of 0, 1 segments? So this has counted everything inside twice, the outside only once. Counts interior 0, 1 twice, counts exterior once. So let's add to this the number of 0, 1 on the boundary. What do we know about the number of 0, 1 on the boundary? Odd. And this is the number of 0, 1 on the boundary. And now we've counted each 0, 1 segment twice. So what can you tell me about this sum? It's even, right? We've counted everything twice. So since we've counted everything twice, it has to be an even number. All right, so we now get that T012 is equal to even minus odd minus even minus even, right? If I just move everything over. The left-hand side has 2 things that are even and 2 things that are odd. The right-hand side is even. You know, T012 has to be an odd number because we have to get an even, and even plus odd, the only way we can make this even by adding 1 more term is we have to add an odd number. So we get T012 is odd. There is a triangle. Well, we're done. This is a beautiful proof. It's one of my favorite ways to show that something happens. You show that, that the count is odd, therefore it exists. What would you say is the next result we would prove? The tetrahedron. If this was a post-300, post-core class, we would probably do the proof in general and have full simplex notation. This is a pre-300 level class, so I'm going to say this hopefully is enough to give you a sense of what would happen. You do not want to see me trying to draw a tetrahedra in 3-dimensional space projected onto a 2-dimensional plane. It gets even worse when you want me to draw 4-dimensional, no. Okay, this is where you start using abstract mathematics. Okay. Hopefully you could see, I get the sense of how we build up from the lower dimension. And as we go up higher, we would have a 0, 1, 2 triangle on the bottom, which would have an odd number of 0, 1, 2 triangles. And then as we try to build up, I think I can see how it would go. As a nice exercise, try to prove that. Try to prove that you can generalize this argument to the tetrahedra. But to me, this is enough to show that something like this is going to happen. It turns out we will be able to use this to find, or to at least prove the existence of fixed points. And so the labeling, right now, the labeling is arbitrary. We're doing it as a game. It turns out that when we do this in practice, the labeling is going to be related to our function that we're trying to find a fixed point on. All right. And the last thing I want to do, we've got about 5 minutes left, is talk about coordinates. I've asked this question before. You understand? Oh, yes.
I have a question about the fixed points thing.
Yes.
Would we also be able to do this in stability? Use using this?
Um,
Or is that, would that be? You don't think it would be this?
I'm not sure. You might have some information. Well, I mean, if it's a contraction map, it has to be stable because everything would have to collapse to it.
Right.
In general, I do not know if you would have anything that's good. That's a good question. If you email me, I'll try to see if I can. Yep. So if you say the wrong thing now, you will flunk this class. What, as a Bostonian, do I have to tip my hat to New York City about, or at least to a subset of New York City? The grids and where? In Manhattan, right? Your Manhattan has a beautiful grid system versus Boston, where you can have, roads like this crossing each other. And in Manhattan, very natural choice of coordinate systems. Your east, west, and your north, south. In a plane, how many coordinates do I need to represent where something is? How many vectors do I need in the plane? 2. And so what I'm going to do, I'm going to do a 3-dimensional coordinate system. And so maybe I'll call this V0, V1, V2. And I'm going to represent something as maybe alpha V0 plus beta V1 plus gamma V2, 0 less than equal to alpha, beta, gamma, and alpha plus beta plus gamma equals 1. Or instead of alpha, beta, gamma, maybe I'll use alpha 0, alpha 1, alpha 2. That might be better notation. Maybe alpha equals alpha 0, beta equals alpha 1, gamma equals alpha 2. When you look at this, this looks like I have a 3-dimensional basis. But because alpha plus beta plus gamma equals 1, how many free variables do I really have? I really only have 2. Once I tell you what alpha and beta is, gamma is forced. So I really have a 2-dimensional basis. And what I'm trying to do is I'm trying to represent any point in this triangle as a special combination of V0, V1, V2. What would alpha, beta, gamma correspond to get to the point V0? It would just be 1, 0, 0. What if I want to get to V1? And then the last one would be 0, 0, 1. And then what you can do is you can show that any point in here is going to be my alpha, beta, gamma. That as I go through all the alpha, beta, gammas that are non-negative and their sum is 1, it's just going to fill in the triangle. And so I can represent any point in terms of these 3. And this turns out to be an extremely useful coordinate system to use. And we will talk more about this next time. Okay.